Direction of arrival estimation is a key stage in automotive FMCW radar, providing target angle in addition to range and velocity. This workshop provides a practical path from DoA theory to real radar measurements and implementation. The path starts with phased array, spatial processing, and the DoA concept, showing how phase differences across multiple antenna elements encode target direction. The theoretical part then introduces the main DoA estimation methods: spatial FFT, Bartlett beamforming, Capon MVDR, music, and ESPRIT algorithms. Their operating principles, assumptions, resolution compatibilities, and practical limitations are examined through numerical examples and simulations. The theory is then validated using a real measurement acquired with the Texas Instruments AWR2243 radar, configured with 8-element virtual ULA using time division multiplexing MIMO. Controlled measurements with corner reflectors make it possible to examine DoA algorithm performance in different radar scenarios and directly compare conventional and super-resolution methods. The provided measurements datasets extend the workshop beyond the presented examples, supporting algorithm comparison, parameter studies, alternative processing approaches, and further DoA development. Using these datasets, the FMCW radar signal processing chain is explained step by step, connecting the theoretical concepts with practical implementation and real measurement data. The workshop is organized as a set of short, self-contained modules supported by many animations. Each topic remains focused and can be studied independently without requiring the complete workshop sequence. All processing scripts are provided in Python and can also be examined with modern AI coding tools. This makes it possible to study individual processing stages, relate the implementation to the theory, and use the existing scripts as foundation for further radar signal processing experiments. The result is complete path from the phased array DoA theory to real FMCW measurements with reproducible processing.